Hello everyone, we are here to present our work on Can Vision Language Models Solve Visual Math Equation? So as a motivation, we try to bridge the gap. How do vision language models learn visual maths? We try to take inspiration from humans themselves. What we do is we try to look at visual equations, right? We try to first count them, try to perceive them, and then we try to reduce them into some abstract symbolic equations and we solve them. We already know that VLMs are strong in tasks like visual question answering and anything involving visual recognition. And the LLMs which are used underlying making these VLMs are getting better and better in solving text-based symbolic math. However, our main question here today is, are VLMs truly reasoning like a human? Do they possess the basic grounded skills like counting required to integrate vision and math? For this, we try to decompose the task into some basic components like we mentioned before. We have three major tasks here. Variable recognition. Are we able to map visual objects to a variable, to an abstract symbol? Secondly, counting. Counting the number of objects to get the coefficients to solve those equations. And thirdly, once we have those equations, we obviously need to solve them. A bit of a spoiler alert, we find that the primary limitation comes for VLMs from its inability to do visual counting, and when we compound it with existing reasoning capabilities to solve math problems, we see a decline in performance. So we move towards a control test for grounded symbolic reasoning. What is our task? Given an image of a system of equations where variables will be represented by object icons, while the coefficients must be inferred by counting those icons. You may ask this question, why this task? Well, the major reason is that it forces a VLM to perform these sequential steps, and we try to analyze these steps. Those are recognition, counting, and symbolic solving. Moving on, once we have our data set ready, as you can see, we evaluate across leading VLM architectures. At the time when we performed these experiments, these were the models available for our benchmark, and our benchmark consists of 1000 generated solvable visual linear equation systems, each 2 variable and 3 variable type. So in total we had around 2000 examples, 1000 of 2 variables and 1000 of 3 variables. And other than that, we also tried to take two prompting approaches. One's the zero shot ability, because we wanted to directly know the answer, and as since you can see all the proprietary models are models which are used in production, which are used in public release, and mostly people asking these questions to a VLM would do a zero shot prompting. However, we wanted to leverage the full power of language models and the vision language models, so we also try to do some kind of a two-step, like a chain of thought process, and where we try to decompose the task ourselves, tell it to extract the coefficients first and then solve. So this is the whole pipeline which we employed. So to create the equations, we first generate the equation using matrix algebra, and we obviously make sure that the equations generated and the solutions have integral solutions. We don't want the VLMs to be at a disadvantage which comes by doing floating point arithmetic operations. So we then use the icons QA dataset to grab some icons, simple visual icons, and then we try to create visual equations as you can see above here. And once that is done, we feed it to the two prompting techniques shown here. The direct prompt is something where we ask the answer directly, and obviously there are some post-processing prompts also, so that we are able to extract the data easily. On the other hand, we have the two-step chain of thought prompting, where in the first prompt we tried to use the VLM to reason and give us the answer, and then we use the final answer prompt to extract that answer. And then we prompt this into the various models which we have discussed before, and then we do a evaluation on it. The evaluation metric here will be accuracy. Basically, if you get the answer right, you get a point. And now we come to the major highlight. We notice that when we come with the visual math equation data benchmark versus a symbolic benchmark, where we try to use the equations written in pictures and the models try to do some sort of OCR, we notice that symbolic equations where the inputs are text put on an image, these models achieve almost near perfect accuracy. That means almost most of the examples they get it right, and that goes same for almost all the models. But the real surprise comes in when we try to put the visual equations in those models. Shockingly, we notice the accuracy dropped drastically across all models, falling to 12% overall, and even lesser. 12% was something which we got the highest. So what we tried to do is we had a chain of thought prompting strategy also, and we tried to deep dive and figure out where it's going wrong, and there we notice the actual culprit. Almost all the examples where the things have gotten wrong were due to the wrong counting. As you can see in this equation, there are 7 apples and 3 bananas, and the second equation has 1 apple and 10 bananas. But the model, the VLM, and this is in case of the Gemini model here, is unable to count correctly and gets the wrong equation from the start, which eventually, irrespective of how many calculations you do, how many optimizations you do, your answer will be wrong. So now we have our failure point identified, which is the counting problem, and to analyze it further, we isolate into 2 visual steps. We try to figure out if it is able to recognize the variable correctly. That is, if it is able to identify the icons, maybe there is an icon mismatch. And on the other side, obviously, the coefficient counting. So for variable recognition, we see, and as we stated before, the visual recognition capabilities are very high. It's able to accurately guess what kind of an icon it is and map it to the correct variable. And when we went to counting, just like we can see in the analysis, upon doing furthermore analysis, we can see that that's the primary bottleneck, that the accuracy plummeted on the direct task of object counting, confirming that it's the main failure point here. And integrating these abilities are even harder, so there are even more compositional errors. So what we try to do is we try to create another variation of our benchmark, where we try to include a visual symbolic setting. So what we do is the icons are as variables and the numeric text act as coefficients. We notice that the accuracy improved, surely, compared to the almost like a near 12% performance, we came to 64%. But then this is still poor compared to the symbolic baseline, which was more than 97%, in some cases 100% also. When we did a further analysis, we noticed, especially in case of counting, as the coefficients went up, the total coefficients, I'm not talking about coefficient of one kind of an icon, but the both kind, basically apples plus bananas in this case. And as you can see, the accuracy goes drastically. So the more things you get to count, the more bad results you get. But looking at the visual symbolic setting, we realize that this is not only about counting, it's also about composing both counting and arithmetic solving. So even when counting is eliminated, the act of combining visual recognition with symbolic calculations introduce around a 30% accuracy penalty. On the other hand, we did a further ablation study where we not only limited ourselves to 2 variables, and as proposed in the benchmark, we also come with a 3 variable system, and we wanted to test the hypothesis whether increasing complexity would break symbolic reasoning itself. And we were on the right track, where we noticed that in a pure symbolic setting, the accuracy drops sharply from 98% to 70%. And beyond perception, what we conclude is that VLMs lack a robust symbolic generalization and fail to reliably solve even slightly more complex mathematical problems. So what we notice is the gap is that VLMs struggle in simple equations already, and when we try to compose these simple equations with more variables, we see more issues upcoming. So the key takeaways which we find from our work here and the benchmark is that number 1, coefficient counting is the primary visual language model's bottleneck, and we call it the perceptual failure. The second takeaway is that there are compositional errors are significant, as there was a huge penalty, at least more than a 20% or 30% penalty. Combining accurate recognition with math reasoning introduces a large penalty, and we call it the reasoning integration failure. And lastly, symbolic reasoning lacks generalization. So even the language models used underneath are still not capable enough as they are claimed to be in solving math equations when more number of variables come in. The math performance degrades sharply as problem complexity increases. and we call it the pure symbolic failure. So together, our benchmark tries to explore and tries to show the perceptual failure, the reasoning integration failure, and the pure symbolic failure for VLMs. And we hope that this allows models being trained for reasoning to counter these lacks. And in future, we hope that we see better performing models. Thank you. Our code and our paper is readily available on the links below. We also have a release coming soon on Hugging Face datasets for the same. Thank you.